Greetings once again, ladies and gents. Today I'm looking at replacing O2 sensors as would be used in an automotive application. What you're looking at is my Bosch 15716 sensor and the tool I used to replace them with. The sensors came from eBay. The tool came from O'Reilly's Auto Parts. When you're shopping for O2 sensors, probably the best thing to do is first find out what the manufacturer's part number that they used is. Then go searching for that part number in the automotive parts stores, Amazon, or eBay to get the best deal. O'Reilly's wanted $50 per sensor. I managed to find the same sensor on eBay for $35 for both sensors. Take your time, shop around. I've generally found out eBay is the lowest cost, but Amazon has beat eBay on occasion. On a rare occasion, I've actually had an auto parts store beat Amazon and eBay. As for the tool, I managed to find this one at O'Reilly's Auto Parts for $15. There are basically two styles of removal tools for O2 sensors, and yes, I definitely recommend you use a tool for removing O2 sensors. This style of tool generally works best when you can reach straight in and touch the nut on the sensor, and then have enough room to wiggle your arm slightly so the ratchet could move just to break the sensor loose. The other style of tool is like an extended socket with one side notched out of it. It's designed to be accessed with a conventional ratchet from the top. It works best when you have plenty of room above the top of the sensor to put the socket on. In my case, side access was far better than top access, so I elected to go with the crow's foot style of tool to remove the sensors. As you can see here, a conventional box wrench will not go over the connector, requiring that you access the sensor from either the side or the top. As you might imagine, since the sensors have been in the exhaust piping for years, they can be extremely tight to get out, making it a real good idea to have a full 6-point contact when you're trying to remove one. Here's my recommended tool set for pulling oxygen sensors. This worked real well from a Mustang, and the sensors were installed in very tight locations, as the next photos will clearly show. I found the best procedure for removal was to first break the sensor loose, then proceed to the connector. Using one hand to hold the connector tab down, you can insert a small screwdriver in between the two halves of the connector and then twist it slightly to pop the connector loose. If there's any resistance, you're probably not holding the tab down tight enough to release the connector lock. In my case, the driver's side sensor was easy to remove. It was a matter of just breaking it loose with a tool and then reaching up with one hand and turning the sensor out. The passenger side was a whole nother access issue. The only way to break it loose was to put an extender on the ratchet and then go for all the torque I could possibly muster from underneath the car. It was completely impossible to get two hands in there. But using only one hand, I couldn't even grab the sensor to turn it. The solution turned out to be to leave the tool on the sensor, leave the ratchet portion up on the top side of the sensor, and reach in with one hand and spin the sensor out using the tool. Now as to why the sensors matter. These charts were derived from my Motes quarter horse as installed on my 1995 Mustang GT, running binary editor on a host HP Vista computer. When the computer first starts up, it runs on saved table data as stored in the computer's memory. Once the engine is up to temperature, it starts looking at the sensor voltages. The sensors are operating in a very narrow range, switching from rich condition to lean condition back and forth again continuously. The computer is looking for that happy median point at around 0.45 volts or 14.64 air-fuel ratio, which is stoichiometric for gasoline. Obviously, if the sensor is bad and the sensor is switching at the wrong points, both gasoline mileage and emissions will suffer. My Mustang uses two sensors, and as you can see from this chart, the synchronicity between the two can vary quite a bit. Based on this sensor data, the computer then calculates a targeted air-fuel ratio. The computer then generates an error function, checking against where it thought the combustion should be versus where it actually was, and then issues a running correction to its data table so it can remember where the correction needed to be at that particular load and RPM for the engine. And just for reference, here is a chart showing instantaneous mile per gallon versus running miles per gallon at a cruise condition of around 45 miles per hour. Well, this here video may be done, but this here engineer ain't. He got a lot more ideas coming on down. If you're liking what you're seeing, give me a like and consider subscribing. I just might have something else coming down here real soon you're going to want to see.